Lesson 21.4 is going to talk about transforming exponential functions. So we're going to be looking at the graphs of these functions and using transformations to make the pictures for these functions. So make sure you have the note sheet that goes along with today's lesson, something to write with, and then since we're graphing, you might want Desmos or your calculator to help you out with some problems. All right, so our parent function for exponential values was this. Y is equal to a times b to the x power. So when we have transformations, that's when we start putting different numbers in our spot. So if we look at this here, this little chart, okay, we start seeing if we have something in the exponent spot, it'll move your function. If we have something at the end that moves our function, and then anytime we have a coefficient in front, that will also kind of do our function a little, make it look a little different. Okay. Now we've done this before with absolute value functions and parabolas, so the rules are still the same. Okay, anytime we have something with the x value, so in this part, it's with the exponent part, that's going to be our horizontal shift. So a minus moves it to the right, and a plus moves it to the left. Okay, also like before, anytime we have a plus or a minus outside the function, so at the end, plus would move it up, and a minus moves it down. Now, anytime we have a vertical shift, this is also going to affect our asymptote. And we'll see that when we actually start doing some graphs here soon. Okay, and that a value in front we talked about the other day, it's called the initial value. So that a value is going to be your shrink or your stretch. So the bigger the number, the more stretched out the graph will be. The smaller the number, the more shrinked down the graph will be. And just remember, anytime we have a negative in front, that's going to flip our graph or make a reflection. So again, the rules are the exact same as they've been every other time we've done transformations. We just have a different parent function. Now, another thing I want to point out is the b value, our base, okay, is not a transformation. The base is just going to tell us growth or decay. Okay. So it's just going to tell us how the graph should look. Should the graph be increasing or decreasing? So let's start by naming some transformations. So again, in each problem, the base value, okay, the b value, in this one it's 5, okay, 1/2, 7, 6. Those are not transformations. Those are just the base of the problem. So the only thing that's a transformation is anything outside of that. So like in A here, the 3 is going to give us a transformation, and the -9 on the outside will give us a transformation. Now, if there's a 3 in front, that's going to stretch our graph. Okay. There's nothing in the exponent spot, so no left or right shifts, but a -9 outside the function is a vertical shift, and minus would move the graph down, going down by 9. Okay, let's look at B here. So I have a negative in front and a +3 in the exponent spot. So anytime we have a negative, that's a flip, okay, or reflection. The +3 on the inside of with the x, okay, that's our left or right shift. Plus would move it to the left. So this graph is going to shift left by 3. Okay, let's look at C. Again, 7 is the base, not a transformation. So we have to look at the what's the 1/3 do, the +1 or the -1 do, and the +6. Well, the 1/3 is a coefficient. That's going to shrink the graph. So it's less than 1. So it's going to shrink by 1/3. The -1 in the exponent spot is going to shift the graph to the right. And then the +6 outside the graph is going to move it up. So shrinks, right 1, up 6. Okay, so I want you guys to do D. Now this one has a little bit of everything. There's a negative in front, a 2, an x +3 in the exponent spot, and then a -8. So go ahead and fill in those transformations. Okay, if you did everything right, the negative will flip it. The 2 is going to stretch the graph. The +3 moves it left, and the -8 moves it down. All right, let's put this all together now and actually start graphing these functions. So sketch the graph of the parent function f and the graphs g and h by applying the correct transformations. Okay, so our parent function here is 2 to the x power, and this base can change. So there's multiple parent functions for exponentials, it all just depends on what the base is. But 2 to the x, 2 to the x minus 3, and 2 to the x plus 1 are all from the same function. They're just going to have different transformations. So what I'm going to do is I'm going to start by graphing f using Desmos, so we could talk about what the parent function looks like, and then we'll use transformations to graph the other two. Let me head to Desmos. Okay, so here's my parent function, 2 to the x. So a couple key points here is you should notice it's not at the origin. Normally our parent functions, we always started at 0, 0. You don't do that with exponentials. So for exponential functions, we actually start at 0, 1. So that's where all of our graphs are going to start. Okay. The other thing we have to point out is our asymptote, as you can see, is this point. As we move it, it gets closer and closer to 0, but we'll never actually cross that line. Okay, so our asymptote here is at 0, 0. Okay, so that's another thing to point out. So let me go back to our notes here and graph this. So the parent function would start at 0, 1. I'm going to do this one in black. And it always has an asymptote at the x-axis. So now all you have to do is put in the curve. Now since it's 2 to the x, would 2 to the x be growth or decay? Well, 2 we know is bigger than 1, right? So 2 would be a growth function. So since it's growth, the function is going to start low by my asymptote, pass through my point, and then shoot upwards. Okay, just like it did on Desmos. See, it starts low by the asymptote, passes through 0, 1, and then starts to increase quickly. Okay, so now if we graph the other ones, we can do it on Desmos, but I'm just going to use the transformations. This graph, since it's 2 to the x minus 3 power, means the graph is going to move to the right. We're going to go right by 3. So I'm going to take that 0, 1 point and just shift it right, 1, 2, 3. Now, if we're moving the graph left or right, you notice if this asymptote moves with the point, it's going to shift left or right, but it doesn't really change the placement of it. So horizontal changes won't really move our asymptote. I want you to think of this point and the asymptote like they're tied together like a string. Okay, if the point moves, the asymptote moves with it. But again, if we're moving left and right, it doesn't really change its placement. Now it's still growth, so I'm still going to start low, pass through my asymptote, and go up. Okay, so there's 2 to the x minus 3. So let's graph one more here. If we have 2 to the x and then plus 1, that's going to move the graph up by 1 value. So starting at my parent function 0, 1, I would shift that point up 1. Now again, if I moved my point up 1, that's also going to move this asymptote up 1. Let's change his color so we can tell the difference. And if that happens, it's still growth, so we're just going to start low by my asymptote and shoot it up. So we have 2 to the x plus 1. Okay. So let me go back to Desmos really quick. You could see here's 2 to the x minus 3. That graph is just shifted over to this point here at 3. Okay. And then if I turn that one off, here is 2 to the x plus 1. So you see how the point just moved up 1 spot, and so did the asymptote. It's starting to level out now at 1 instead of 0. Okay. So let's put everything together now on the back side and actually graph some of these functions. So in A, we have 1/2 to the x minus 3 power. So remember that 1/2 is just our base. It's not a transformation. So the only transformation it looks like I really have is that minus 3 in the exponent spot. So that's going to shift our graph right 3. Okay. Now if it's 1, we'll worry about this part in the end here, but normally the parent function starts at 0, 1. And the asymptote would be on your x-axis, like that. Okay. So if we shift our graph right 3, 1, 2, 3. My new point is here. Again, the asymptote didn't change locations because if we just move it left or right, it's still going to be at 0. So now we just have to put in our curve. Now 1/2 is less than 1. This graph will be decaying or decreasing. So you got to start high, pass through your point, and kind of level off by your asymptote. Okay, so since our asymptote didn't change, it's still at 0. Okay, and then if we talk end behavior, the left side's going up forever. So that means y would be approaching positive infinity. As the graph moves to the right, it's going to level off by our asymptote, which is at 0. Let's do another one. This one is 4 to the x power, x plus 1 power, and then minus 2. So I know x plus 1 is going to move the graph left. So we're going to go left by 1. And then we're going to go down by 2, minus 2. Okay. Now let's look at our function here. Normally the parent function would start at 0, 1. We have our asymptote at the x-axis. So now let's put in our transformations and see how the graph moves. So if we go left 1, down 2, here's my new point. And then the asymptote has to move with that point. So if this graph goes left 1, then it's going to go down 2. The asymptote will shift as well. So again, think of the point and the asymptote like they're connected by a little invisible string. The point moves, your asymptote moves. The only thing that's different is if it's moving left to right, it doesn't really look like it's moved, but when it moves up and down, you can definitely tell. All right, now let's put in all of our key features here. If it's 4 to the x power, that's exponential growth. So that means our function is going to start low, pass through my point, and then increase. So there is our function. So again, it helps me to put a little x by the starting point because then I can see exactly where I shift from. So the only point I really care about you guys have is making sure you have the right point in the right spot, and you have to draw on this asymptote. So make sure you have your asymptote drawn, your point, and you have the right shape to the graph. So this one, our asymptote, since it moved down 2, is at y equals negative 2. The left side is approaching that asymptote, so y is approaching negative 2. On the right side, it's increasing forever, so that would be approaching positive infinity. All right, I'm going to do one more with you. So this graph, we have a couple things going on. Again, if we look at the 1/3, that's just the base of our exponential function. It is not a transformation. So let's look at what we got. We have a negative in front, which will flip the graph. I have a 2 in front, which is going to stretch the graph. Okay. And then we have that plus 1, which is going to move the graph to the left. Left 1. Okay, so this one's going to be a little tricky because of the stretch, so just watch what I do. Okay, so our graph would start at 0, 1, the parent function, and our asymptote would always start at the x-axis. So here's what's going to happen. When our graph flips, my point is going to flip over my asymptote, and now it's at 0, negative 1. But when we stretch that point, it actually is going to move it to negative 2. So here's what I always say, okay, that the first value, the a value, is always our initial value, aka where we start the graph. Okay. So if this graph is going to, normally it would start at 1, but the initial value, the a value that gets stretched, okay, is telling us instead we're going to start at negative 2. So that didn't apply for the graphs above because we didn't have a coefficient to start it at. But in the future, anytime you have a coefficient in front, that's always your starting point. So you would start at negative 2 and then do your transformation. So we did negative 2. We have to go left 1. So here's my point. And now we just have to envision what this graph is going to look like because the flip is going to make it look a little different. Now, normally, if we see 1/3, we would say that that graph is decaying, right? It would look like this. So then if I flip this graph, I'm just going to use my computer here to do that. If I flip this, it's it's going to make it look like this. So this is actually a growth problem because it's going to actually be increasing. So again, the decay, when it's flipped, will look like this guy. So we would take the graph and we're going to start low, pass through my point, and then level off towards my asymptote. My asymptote didn't move since we didn't have any vertical shifts. It's still at 0. Okay, as the graph goes to the left, what's y doing? It's going down forever. And as the graph moves to the right, well, it's going to approach our asymptote from underneath, so it's going to approach 0. Okay. So I'm going to have you guys try this number or letter D. So you have 3. Okay, 3 to the x minus 3 power plus 1. So start with what are your transformations? And again, 3 is not a transformation. 3 is the base. So you have 2 transformations. What does the minus 3 do? What does the plus 1 do? Start your graph off at 0, 1, and then do your 2 shifts. So let's see what you get for your graph here. Okay, if you did everything correctly, here's what I have. So again, normally the graph starts at 0, 1, but I shifted my point right 3 and up 1. So that also moved my asymptote up 1. So my asymptote should be at positive 1. 3 is bigger than 1, so there should be exponential growth. So it starts low, passes through your point, and then increases. And then if we just put in our end behavior here, you should have had that. On the left, y is approaching your asymptote, so y is approaching 1. And on the right, it's going up forever. Okay. So that is how you graph. So again, graphing transformations, start at 0, 1, put in all of your transformations. The only time it gets really tricky is when you have a shrink or a stretch. So we could practice those more in class tomorrow, but that is how you graph transformations of exponential functions.